Okay. Hi, everyone. Welcome to the final seminar of the Clever Planet seminar series for this semester. Today we have Megan Newcombe with us. Before introducing Megan, I'm going to spend a couple of minutes talking about the Clever Planets Consortium as well as a land acknowledgement statement. So Clever Planets is a multi-institutional interdisciplinary initiative to unravel the conditions of planetary habitability in our solar system and beyond. Its lead institution is Rice University and is supported by NASA. It's one of the teams of the Nexus for Exoplanetary Science System Coordination Network under astrobiology. And it's a brief land acknowledgement statement. Our research at Rice University is pursued on the traditional territory of several native peoples, namely the Karankawas and the Sanas, as well as the Cohicutans, represented today by the Tap-Talam Cohicutan Nation and the Ishaks, represented today by the Atakapa Ishak Nation. We see as a duty to acknowledge the historical aspect of our identity and to foster a beneficial environment for all communities, in particular those who preceded us on this land. So it's my great pleasure today to introduce a speaker, Megan Newcombe. So Megan did her bachelor's and master's at University of Cambridge, followed by a PhD at Caltech, working with at Stoper. She was a geophysics postdoctoral fellow at Lamont Earth Observatory at Columbia University, and again followed by another postdoc as a DTM postdoctoral fellow at the Carnegie. She's presently an assistant professor at the University of Maryland. Today, she's going to talk to us about her most recent project that is based on the efficient degassing of planetesimals during melting and differentiation, and it has implications to the water delivery to Earth via unmelted material. So Megan, the platform is all yours.
Thanks, Dan. So let me just share my screen. Okay. So thank you very much for the invitation to talk here today. This is actually the first time I'm presenting this work in a full seminar format, and it's exciting to be able to present it to such an interdisciplinary group of planetary sciences. So today's talk is about how efficient degassing is during melting and early differentiation of planetesimals. And the main motivation behind this talk is to think about where Earth's water came from. So there are a number of possible sources of Earth's water. We know we accreted these planets in a solar nebula that was very rich in hydrogen. So ingassing of this hydrogen-rich nebula material could provide water in planets. We also have these icy rich bodies, comets, flying around. And so potentially these could provide a source of water to the terrestrial planets. And then we have the rocky materials that were accreting from the nebula material itself. And so we can start to work out what the contributions of these different potential sources might be by studying their isotopic compositions. And this work has been done, I'm showing here a compilation by Conal Alexander from 2017. And you can see if you look at the nitrogen isotopic composition and the hydrogen isotopic composition of these different solar system materials, they are quite disparate. So in the top right here, we have the comets. These are the Jupiter family comets, and these are the Oort cloud comets. And you can see that they have extremely heavy nitrogen and hydrogen isotopic compositions. On the bottom left, we have the solar composition, which would represent the composition of nebular materials. And so this is extremely light in its nitrogen and hydrogen isotopes. And neither of those sources look much like the Earth, which is at 0, 0 on this plot in the middle of the diagram. And so the isotopic compositions of comets and nebula gas don't provide a good match to the isotopic composition of water we find on the Earth. And we can kind of rule them out as major contributions of terrestrial water. And in case you are wondering, I'm always tempted to draw a straight line between these things and say, oh, maybe you could mix the nebular hydrogen with the comets and come up with something terrestrial. But as it happens, mixing on these diagrams is very nonlinear, strongly curved. And so if we mixed nebula composition and comet composition on this diagram, you end up with this strongly curved mixing curve. And so we can kind of rule out solar and cometary material as major sources of terrestrial volatiles. So instead, we want to look to these kinds of sources, our planetesimals and our planetary embryos, and think about their accretion and differentiation processes and how that might affect the concentrations of water in the terrestrial planets. So to study those early planetary building blocks, we want to look at the meteorite record. So meteorites provide us with an incomplete sample of early solar system rocky bodies. And there are some different types of meteorites in our terrestrial meteorite record. And one of the most important types is the chondrites. So these you can think of as being cosmic sediments, and they are materials that accreted from the nebula and have not melted. So they have different components in them. They contain these distinctive chondrules, which are kind of millimeter scale round features here that you can see in the picture on the left. They also contain refractory inclusions and a matrix that's very volatile rich. Now, they've all experienced some degree of thermal and aqueous alteration because some amount of alteration is required for them to lithify and form a coherent rock that's unlikely to get broken up in space. But none of them have experienced melting. We then have the primitive achondrites. So these achondrite meteorites have experienced low degrees of partial melting, and they have bulk compositions that are similar to chondrites because they haven't undergone enough melting to have experienced significant metal silicate differentiation. And examples of these primitive achondrites include the uralites, the braconites, acapulcoites, and lodronites. And on the left here is showing a picture of an olivine-rich uralite. And then finally, we have the achondrites. So these are meteorites from planetary bodies that experienced extensive melting and metal silicate segregation. And it's thought that most of these likely had a magma ocean. And so examples of achondrite meteorites from our record include these HEDs, which are from Vesta, the Angrites, the Aubrites, lunar meteorites, and Martian meteorites. So in the past 10 years, scientists have found that all of these meteorite families fall into two groups when you look at their isotopic compositions. And this is described as an isotopic dichotomy. So I'm showing here a diagram of cap 17 oxygen against epsilon 54 chromium. And you can see that two clear distinct groups of meteorites are shown on this diagram. On the left in red, we have the most of the achondrites. We have ordinary chondrites, enstatite chondrites, and achondrites in this group. And this group is denoted the non-carbonaceous group. And it's thought to be bodies that formed in the inner solar system. And then on the bottom right here, we have this blue group, and this mostly consists of the carbonaceous chondrites. And there are a few little weird achondrites mixed in here. Okay, and these are thought to have formed in the outer solar system. There's some debate as to how this dichotomy formed, but it's thought that we need spatial segregation in the disk in order to preserve evidence of this isotopic dichotomy. And so this model produced by Nana et al. In 2019 proposes that there was a change in the composition of material that was infalling to the accretionary disk over the course of early solar system evolution. So they propose that the early infall material was enriched in supernova-derived nuclides, and then this material was pushed out by outflow. And then the later infalling material changed its composition and became more depleted in supernova-derived nuclides. And if we just carried on mixing, then the evidence for this dichotomy would have been erased. But instead, we think that Jupiter formed early enough to spatially segregate these two reservoirs and prevent them from mixing extensively. And it's this formation of this Jupiter barrier that has preserved evidence for this isotopic dichotomy. So why am I talking about all of this? How does it relate to the volatiles? Well, because there's this proposed spatial segregation between these two reservoirs, and we think that the CC reservoir accreted in the outer solar system and the NC reservoir accreted in the inner solar system, these two reservoirs are also linked to volatiles because the outer solar system bodies accreted in the presence of ice beyond what we call the snow line. So the snow line marks the point in the accretionary disk where beyond the snow line, ice is stable, and within the snow line, it's too hot for ice to be stable. So this has led to this hypothesis that inner solar system bodies would have accreted water poor, and outer solar system bodies would have accreted water rich. And this kind of became problematic for thinking about why we have water on the Earth in the first place. If we accreted in this dry inner solar system environment, then it's hard to explain why we have oceans now. And so people have worked on developing models to explain the presence of water on the Earth. And one of the more popular models is this Grand TAC model, or there are variants on the theme, but most of them involve delivering volatile-rich material from the outer solar system into the inner solar system as the Earth was accreting. And the Grand TAC is a variant on this model that says that the scattering of water-rich carbonaceous chondrite material occurred when Jupiter migrated in and then out and caused mixing of this water-rich material into the inner solar system. So does this delivery of carbonaceous chondrite material make sense when we think about the isotopic composition of Earth's water? Well, yeah, it does. So if we look at this diagram here, you can see that all of these inner solar system bodies, the Earth, the Moon, Mars, Vesta, and the Angrite parent body, they all lie in this region of the diagram, and they overlap in their composition with the carbonaceous chondrites. And so we have a good isotopic match between carbonaceous chondrite water and the water that we're seeing on all the terrestrial planets. Furthermore, if you look at the volatile budget of the Earth, you can explain the volatile budget of the Earth by adding 2 to 4% of carbonaceous chondrite material to a volatile depleted proto-Earth. So here is some volatile data compiled by Conal Alexander, and this gray band here represents 2 to 4% CC addition to a completely dry volatile depleted proto-Earth composition. And these data points here are the bulk volatile content of the Earth. And you can see that for most of these volatile elements, there's a good match between just adding carbonaceous chondrite material to the concentrations of the volatiles that we see in today's bulk silica Earth. Now, there are a couple of wild exceptions on this plot. So you'll notice there's a bit of a problem with nitrogen and xenon. And in this particular paper, they propose that perhaps there are some issues with the measurement of nitrogen in the bulk Earth, and perhaps xenon is lost into space. But I think there are probably other possibilities, and I'm sure your group has many ideas about this as well. But in general, most of the volatile elements are a good match to carbonaceous chondrite material. Another study that looked at the Angrites also provided pretty strong evidence, I think, for delivery of carbonaceous chondrite material to the inner solar system. So if you look at the volatility curve for the Angrites here, we're plotting concentrations that are normalized to see achondrites against these 50% condensation temperatures, which are a proxy for volatility. So on the right here, we have the highly volatile elements, hydrogen, carbon, and nitrogen. And then on the left, we have the refractory elements, things that aren't easily volatilized. And so you can see that beyond silicon, these elements have been affected by some volatile loss. And they've drawn a dash curve here that indicates what you would expect from just a very volatile depleted body. But the highly volatile elements are more enriched than you would expect for just something that is degassed its most volatile elements. And furthermore, the concentrations of hydrogen, carbon, and nitrogen are similar to more moderately volatile elements like rubidium. And in fact, you can get a good match to the Angrites data by assuming that you have a volatile depleted parent body that then has around 0.3% carbonaceous chondrite material added to it. And so that's this green curve here. This is what you would get if you added 0.3% CC material to a volatile depleted parent body. Okay, so this all seems to work. So does that mean we can close this case and move on? Maybe we just have late delivery of carbonaceous chondrite material. Well, there are a few other issues that we need to tie up. So one is that late delivery models assume that the terrestrial planets are accreted dry. But we have a record from non-carbonaceous chondrites, the ordinary chondrites, the enstatite chondrites, and the achondrites. These are accreted in the inner solar system, but they do contain volatiles. So perhaps it's not safe to assume that the initial accreted material was completely dry. And we also have not definitively demonstrated what happens to volatiles during melting and metamorphism. So as you're accreting material to a growing planetary embryo, are the volatiles going to be lost during that process, or can you retain them? And a couple of studies that have come out recently suggest that, yeah, maybe we are accreting water just in the inner solar system and we don't require this delivery of carbonaceous chondrite material. So this study by Piani et al. From 2020 says that Earth's water may have been inherited from materials similar to enstatite chondrite meteorites. So they've done bulk measurements here of the water in enstatite chondrites, and they find that enstatite chondrites have relatively high amounts of water. And interestingly, if you look at the Angrites here, which are the differentiated equivalents of enstatite chondrites, they're also finding significant amounts of water in these differentiated Angrites. So these lines of evidence point towards just primary accretion of enstatite chondrite water as a way of explaining Earth's water budget. So this throws up the question of, did Earth obtain its water during primary accretion? And perhaps differentiation and melting are not leading to significant water loss. And then some other recent studies have begun to propose achondrite meteorites as an important source of Earth's volatiles. So this study here by Hirschman from 2016, they have various kind of mixing models, and they propose in one of these models that a late veneer composed of 80% urolite material and 20% CI could be a potential source for Earth's volatiles. So what we want to test in this work today is whether water and other volatiles are retained during melting and thermal metamorphism. And this will help us to answer the question of, does the presence of water in achondrite meteorites, things like the Angrites, does that require late delivery of carbonaceous chondrite material? And so to answer this question, we've analyzed volatiles in two different sets of meteorites. So the first set of meteorites is a set of rare, ungrouped achondrites that are accreted in the water-rich carbonaceous chondrite region. So because these are accreted beyond the snow line, we know they are accreted in the presence of water and ice, but did they retain those volatiles during melting and differentiation? And then the second set of samples we're going to look at is the primitive achondrites, and we're looking at the uralites, which are one of the most common meteorite groups that we find on the Earth. And we know that they partially melted, but there's strong evidence that they never had a global magma ocean. And so this will test the hypothesis of whether a magma ocean is required to outgas volatiles, or can we move this volatile depletion back a stage to the point where we just have incipient thermal metamorphism and melting. Okay, so to begin with, let's talk about these carbonaceous chondrite materials, these rare achondrites that formed in the CC region beyond the snow line. So these rare ungrouped achondrites fall into that carbonaceous chondrite group that I showed earlier on. This so they follow the same kind of isotopic dichotomy that we've seen from all of the others on a plot of cap 17O against epsilon 54 chromium. But unlike the rest of the members of this CC group, they have undergone melting. So we have analyzed the volatiles in a selection of these ungrouped achondrites, some of which formed in the carbonaceous chondrite region, and some of them that have non-carbonaceous affinities. Okay, so you can see just from looking at these pictures that most of these meteorites contain mafic phases like olivine and orthoperoxine. And they appear to have relatively primitive compositions. And so we don't think that they formed from extracting a partial melt and recrystallizing. And so examples of this are Northwest Africa 6704 and paired meteorite Northwest Africa 10132. So because these are ungrouped and they're rare, there's not a huge amount of chemistry that's been done on these meteorites, but 6704 is an exception. We do have whole rock data for this meteorite. And you can see that its composition is approximately chondritic in all but the most volatile elements. So this is evidence that we haven't got segregation of the highly siderophile elements. And so there's evidence that we haven't got extensive differentiation or metal silicate segregation on this parent body. The other two kind of unusual ones on this compilation are 8409, which is a gabbro, and 11558, which is an andesite. And so both of these represent crustal lithologies. These are likely from parent bodies that did undergo silicate differentiation. So our methods, we've used secondary ion mass spectrometry to measure the volatiles like water, CO2, fluorine, chlorine, and sulfur, mostly in nominally anhydrous minerals. And so here's a picture of the SIMS at Carnegie that we used. And on the right, I'm showing a calibration curve for our chloropyroxene measurements. So you can see that we've measured OH and we've ratioed it to silicon. And we have this nice new set of standards from Kumamoto et al. 2017 that give us a really nice calibration line to work from in this pretty low water concentration range from 0 up to just over 200 parts per million water. Okay, so I want to talk a little bit about how we use water concentrations or in nominally anhydrous minerals to constrain the water contents of a coexisting magma or even a parent body, because this isn't as direct a measurement as a bulk measurement or a measurement of a melt. So nominally anhydrous minerals incorporate what I'm calling water as hydrogen or protons. And these protons charge balance defects in the crystal structure, but they are not incorporated as a main structural component. So water is very incompatible in these elements, and its partitioning in the elements can be described by a constant called a partition coefficient. So in the case of olivine, we can, the partition coefficient is defined as the water concentration in olivine divided by the water concentration in the equilibrium melt composition. And that partition coefficient is extremely low. So for olivine, it's around 0.001. And this has been determined experimentally, for example, by Harry et al. In 2006, and also by measuring natural melt inclusion olivine pairs. So to give you some intuition here, an olivine containing 10 ppm water would be in equilibrium with a magma that contains 1 weight % water, or 10,000 ppm water. And so if you want to find out or think about what the water concentration of a magma in equilibrium with a given olivine is, you just multiply the water that you measured in your olivine by a factor of around 1,000, and you won't be too far off the water content of the coexisting magma. Similarly, in CPX, we can also describe the water partitioning between CPX and an equilibrium melt using a constant partition coefficient. And in this case, the partition coefficient is slightly bigger. It's about 0.01. And so this means that a CPX containing 100 ppm water would be in equilibrium with a magma containing 1 weight % of water. And so in general, you can multiply whatever water content you measure in a CPX by a factor of around 100 to find the water in the coexisting magma. So I hope you guys have been listening, because I made you a quiz. So this is an opportunity for me to have a 30-second break and for you guys to refine your intuition about how these things work and what kind of range of water contents you might expect to see when you're measuring olivines and clinopyroxenes that have crystallized from melts. So I'll give you 15 seconds and then I'll tell you the answer. And if anyone's brave enough to write their answers in the chat, and if you get it right, then I'll buy you ice cream next time I see you at LPSE. Okay, Anna's very brave. So Anna, I owe you an ice cream. All right, so let's have a think about this then. So for question 1, okay, so we have a mid-ocean ridge basalt that contains 2,000 ppm water. And so in an olivine, we'd want to divide that number by 1,000. And so Anna's right, you would expect only 2 ppm water in a coexisting olivine. And in a CPX, we would divide that by 100. And so a morb CPX, you would expect to contain 20 ppm water. And then has anyone done the chondrites? Morb is a good reference point for all of us, right? It's the most common magma on the Earth. But I feel like CI chondrites provide a kind of estimate of what's the upper bound of the amount of water that you might expect in these phases. So a CI chondrite contains around 14 weight % water, or 140,000 ppm. And so, and if you just flash melted a CI chondrite and grew an olivine from that melt, then you would expect 140 ppm in an olivine coexisting with a CI chondrite melt composition. And for CPX, we divide by 100, so you get 1,400 ppm in a CPX coexisting with a CI chondrite melt. So as a little PSA, I hope this is like calibrated your intuition, and we should all be on the lookout for olivine analyses with more than around 300 ppm and CPX analyses with more than around 1400 ppm. Because if you're seeing really high values like that, it indicates that maybe there's some problem with high backgrounds in your analyses, or maybe you're analyzing something like a tiny melt inclusion got into the beam path. But really high values like that kind of require some kind of explanation. Yeah, so hopefully that's calibrated our intuition for how this system works. And now let's look at some data. So first of all, let's think about what our analytical blank is. So we've determined our analytical blank by measuring two very dry materials. We have synthetic forsterite that we really think has around 0 ppm water. And we also have supersil glass, which has been used as a blank by many lab groups for a long time. And over several sessions now where we've measured both of these materials together, we are seeing a consistent 2 ppm offset between synthetic forsterite and supersil glass. And actually, we're using this as a kind of quality control. So if we can reproduce that 2 ppm offset, then we know that our measurements are good enough to be able to look at water contents on the order of 1 to 2 ppm. So that gives us some confidence when we see that 2 ppm offset between these two dry materials. Okay, so plotting my data on top of this, you can see that all of the nominally anhydrous minerals that I measured in both the carbonaceous and the non-carbonaceous achondrites contain less water than supersil glass, so less than 2 ppm water. I've measured a variety of phases here. We've got olivine, orthopyroxene, plagioclase, and clinopyroxene, but all of them are similarly dry. And if I blank correct these data, well, if you noticed on the previous slide, some of these materials look like they had even less water than my 0 ppm synthetic forsterite blank, which likely indicates that A, they're very dry. I mean, it's possible that synthetic forsterite has some amount of water in, but unlikely. My feeling is that this is more likely to indicate a matrix effect between the olivine blank and the other minerals that I've been analyzing. So, matrix effects can affect SIMS analyses, and what you really want is for your standards to have a very similar major element composition to your unknowns. And in this case, we have a slight difference. So effectively, our blank corrected data let us place a very conservative upper bound of 2 ppm in our meteorite nominally anhydrous minerals. And that's based on the detection limit of 2 ppm in my higher blank session. In this other session, I actually got down to 0.6 ppm detection limit. And so for the meteorites on the left here, these materials here, we can say that they had an upper bound of 0.6 ppm water. So these are among the driest measurements of nominally anhydrous minerals ever. If you look at this compilation by Pellier et al. From 2010, you can see that most terrestrial orthopyroxenes, for example, have an average of around 160 parts per million water, and there really aren't very many down at the low water end. If you look at other analyses of achondrites we have on here materials from the moon, the HEDs and Angrites and Mars, and these are our results on the left here. So our ungrouped achondrites that we've analyzed are drier than any other solar system material that we found. And in particular, they're drier than nominally anhydrous minerals from the moon. So these things are extremely dry. To dry this home even more, here's a comparison with an olivine measured from an Angrite that was published by Adam Sarafian and others in 2017. So the water data here is in blue. You can see this olivine contains up to 20 ppm water, and down to around 6 ppm water. And if I add our results on here, our primitive achondrite olivines have less than 2 ppm, so they're way down at the bottom of this plot. So we can use our partitioning relationships to constrain very conservative upper bounds on the amount of water that could be in a coexisting silicate melt. So some of these end up being more conservative than others. Our best constraint on this diagram is this 26 ppm water, which actually comes from a melt inclusion analysis that we made on this meteorite. And then the 700 ppm, that's constrained from 2 ppm in an orthopyroxene. And these 200 ppm values are from 0.6 ppm in an orthopyroxene. So in general, we have very, very low water contents, even in the coexisting magmas. So our results from this section suggest that water is very efficiently lost during melting and thermal metamorphism on planetesimals. Okay, so we've looked at part 1 here, and we can say that, we know these CC meteorites accreted water. Did they retain the volatiles during melting and differentiation? No, they did not. They have really lost most of their water. So now we're going to move on to the second part, looking at primitive achondrites and this family of meteorites called the uralites, which we know only partially melted and never had a global magma ocean. So we're going to test our second hypothesis of, is a magma ocean required to outgas volatiles? And this work has been done by my graduate student, Liam Peterson, and he actually just recently got awarded a NASA Finest grant. This is a future investigator grant to do this work. And so, yeah, we're excited to show you these early results. So to give you a bit of background about the uralites, these are carbon-rich meteorites. They contain around 2 to 7 weight % carbon, and they're thought to be mantle rustites that underwent around 15 to 25% partial melting. You can see in these pictures here, they're mostly composed of olivine and clinopyroxene with a bizarre graphite matrix, which suggests that they equilibrated under very reducing conditions. They keep getting weirder. So the uralites, if you plot them in oxygen isotope space, we're looking here at cap-17 oxygen versus delta-18 oxygen. Most parent bodies on this diagram define a very narrow range of cap-17 oxygen. But the uralites have this huge range. And since cap-17 oxygen is a mass-independent signature, this range likely reflects a nebular origin, and it indicates that the uralite parent body did not have a global magma ocean, and it wasn't able to homogenize this variable nebular signature that you see in the oxygen isotopes. And other recent measurements, so this is from Barat et al. 2017. They've looked at cap-17 oxygen, but also delta-13 carbon. And they find that there are several isotopic signatures that vary with olivine core composition. And it looks in all of these different isotopic signatures that there is mixing between two N-member compositions, which they've labeled A and B on this diagram. And so we have incomplete mixing of two nebular reservoirs. So in general, these uralites are capturing an early stage of differentiation on an early formed parent body. We have evidence that the uralites accreted within 1 million years of the start of the solar system. They underwent only limited differentiation. They certainly didn't have a global magma ocean that would have mixed all of those isotopic signatures together. And then they were disrupted early as well. So this parent body was disrupted at around 5 MA. Another reason that we were motivated to look at the uralites is that it's been pointed out that uralites and Earth have a very similar carbon to nitrogen ratio. And in fact, a couple of studies, that Hirschman 2016 study and also Barat et al. 2017, have proposed that urolites could be an important source of terrestrial volatiles. You'll notice on this diagram that, while the carbon and the nitrogen are well constrained and provide a good match to the kind of pattern we see in the Earth, they do not have hydrogen data. So Liam really wanted to fill in this gap and work out what the hydrogen budget of the urolites is. So here are Liam's results. He's measured here water concentrations in olivines and clinopyroxenes from the urolites. And the olivines contain less than 10 parts per million water, and the clinopyroxenes contain less than 6 parts per million water. Liam's done a simple batch melting model to constrain what the water content of the urolite parent body might have been, considering that these are thought to be restites produced by around 15 to 25% of partial melting. So if we run these through a batch melting model, we find that the initial urolite parent body might have contained just 29 to 240 parts per million water. So these are really hydrogen depleted. Because of their high carbon content, lots of people have proposed that they might have had a precursor similar in composition to C. achondrites. And if you take C. achondrites as a starting point, then Liam's results suggest that these main group urolites have lost 99.999% of their accretionary water. So here's his hydrogen data. And we've got about a ratio of about 10 to the minus 5 when we divide by CI composition. Further evidence of this dramatic hydrogen degassing comes from looking at hydrogen-carbon ratios in these things. So here is a compilation of hydrogen-carbon ratios in lots of different meteoritic materials. We have on here the carbonaceous chondrites, and we have chondrites from the inner solar system, like the enstatite chondrites and the ordinary chondrites. And then we have the Earth in the green star and the Angrite parent body in the red square. And here's the urolites way over here. So unlike all of these other solar system materials that have a hydrogen carbon ratio of around 0.3, the urolites are just strongly depleted in hydrogen. And so, yeah, this is evidence that the hydrogen is strongly degassed, and also that hydrogen degassing was decoupled from carbon in the urolites. And this is likely because the urolites are very reducing environment, and so the carbon exists as refractory graphite. And so the reducing conditions we see on the urolites produces decoupling between hydrogen and carbon degassing. So to summarize, the urolites that Liam has analyzed are strongly hydrogen depleted, even though they didn't have a global magma ocean. So the urolite hydrogen divided by C. achondrite hydrogen is around 10 to the minus 5. And I wanted to put it on this plot, but I couldn't even fit it on the scale. We go off scale here down to 10 to the minus 5. So again, this underlines that water is very efficiently lost during melting and thermal metamorphism on planetesimals. So we've tested these two hypotheses. Materials that we know accreted water did not retain their volatiles during melting and differentiation. And the urolites only partially melted, and they never had a global magma ocean. And so we can say that no, a magma ocean is not required to outgas volatiles, but volatiles can be outgassed during earlier heating and melting events. So what are the implications of these results? Well, the results suggest that water is very efficiently lost during these early stages of melting and thermal metamorphism. And so we should think about why these primitive achondrites are so dry. And I like this schematic by Lindy Elkins-Tanton that shows a kind of planet accretion process. And so there are many reasons why these primitive achondrites might have dried out. First up, we have baking by 26 aluminum decay early in the solar system. So we have a rapid decay of this isotope that produces a lot of heat. And this drives melting, but also thermal metamorphism. We could also have flash melting by impacts, causing degassing of volatiles into space. And it's really only once you get to a large planetary embryo size that you can retain your atmosphere even during melting. So we wanted to ask the question, how large does a planetary embryo need to be to retain hydrogen? And so that's what I'm attempting to do with this figure here, where I've got the radius of a planetesimal on the y-axis and the mass of the planetesimal on the x-axis. And these black lines here are lines of constant density. And so you can see at the top, it's low density bodies, and the Moon, Mars, and the Earth, these have bulk densities somewhere in the middle of around 3,000 kilograms per meter cubed. And I've then plotted on it in these colors. This is the critical radius or mass that is required to retain these different volatile element species. And so how did I calculate that? Well, it's a very simple approach that it equates the surface escape velocity to the mean velocity of a gas molecule in a vapor. And it's an equation that I think has been used for a long time, but was written up really nicely by Young et al. 2019 recently. So it says that the critical radius required to keep a vapor molecule on the surface is 3/4 times the square root of 2 times the Boltzmann constant times temperature divided by pi times the mass of a single gas molecule times the density of the parent body times the gravitational constant. So that's how I calculate this critical radius value. So you can see from this diagram that you need around 2,000 to 4,000 kilometer radius to retain hydrogen as molecular hydrogen. And you need around 700 to 1,500 kilometer radius to retain your water and methane. Okay, so melted planetesimals are dry. And so let's think again about how Earth got its water. And so option 1 is that you deliver unmelted chondritic material to the proto-Earth just during the final stages of accretion, where the Earth mass is bigger than the mass of around Mars. And this is based on this previous diagram where I've worked out that really you need to be about Mars size before you retain hydrogen. Depending on the speciation of the vapor, maybe this is an upper bound. Maybe we can tolerate smaller radii if we think we're degassing something like methane. Okay, so I'm showing here the results of thermal modeling by Lichtenberg et al. From 2019, which begins to constrain, how do you get unmelted material in the early solar system? And it depends a lot on the amount of 26 aluminum that you expect to accrete in your growing planetesimal. And that scales with the radius, because if you have a larger radius planetesimal, then you expect more 26 aluminum to be present in that planetesimal. So this diagram was built to explain not just our solar system, but other solar systems that could have different initial concentrations of 26 aluminum. So for our purposes, we can ignore everything higher than 0 on this plot, because 0 is our solar system. That's our initial concentration of 26 aluminum. So if we accreted a planetesimal at time 0, at the very beginning of the solar system, then that planetesimal could grow to a radius of around 10 kilometers. And at that point, it would begin to melt and really outgas most of its water. If you accreted a planetesimal a little later, maybe around 1 million years, then you could get to maybe a radius of around 30 kilometers before you drive significant melting and dehydration. And then if you accrete things later on, like after 2 million years, then the size doesn't matter so much because most of your 26 aluminum has already decayed. So the results of this work suggest that if you have early formed bodies, things that have accreted within 1 million years of solar system formation, then really you need radii of less than 20 kilometers to avoid melting and desiccation of those bodies. Another option that was published by this group, this is Daman's paper from this year, suggests that you could have instantaneous accretion of Mars-sized planetary embryos followed by differentiation. So the idea here is that you want your planetesimal or your planetary embryo to be big enough by the time it starts melting that it has enough gravity to retain an atmosphere. And this model was developed for nitrogen, but I think it could also work for hydrogen. With a combination of this with our results and the thermal modeling that I just discussed suggests that the planetesimal building blocks of these embryos have to be small. They have to be less than around 20 kilometers radius if they're forming within 1 million year of solar system formation. Okay, so I want to summarize now. We've analyzed volatiles in carbonaceous and non-carbonaceous achondrites and primitive achondrites. And these samples that we've looked at represent the very earliest stages of planetary accretion and melting. They're dry. This is quite a simple story. They're really, really desiccated. And this suggests that degassing of planetary embryos during 26 aluminum heating and impact events is very efficient. And so we would support models where water is delivered to Earth via unmelted material. And if this material accreted within 2 million years of CAIs, the beginning of the solar system, then only planetesimals smaller than around 20 kilometers are expected to remain unmelted and retain their water. And finally, a carbonaceous chondrite signature does not necessarily indicate water-rich material. So the fact that we have measured material that we know accreted in the outer solar system, but it's really dry, that could be important for future models of volatile accretion to the Earth that use this C signature as a proxy for volatiles, because we know that at least some of that CC reservoir is dry. Okay, so with that, thank you very much. And thanks also to my collaborators on this project. And I'd be very happy to discuss this with any of you guys.
Thanks, Megan, for this absolutely amazing talk. The floor is open to questions from the audience. And you can either raise your hand or you can type your questions in the chat box and I'll read it out to Megan and she can. So Maxime has a question. Yeah, Maxime, go ahead.
Yeah, thank you for the talk. I have a question about how you compute the radius for retaining an atmosphere. In particular, you written this equation where you see that it's proportional to a square root of temperature, and I was wondering which temperature you were using there.
Oh yeah, yeah, that's a good question. So we assumed for that calculation, we assumed a temperature of 1000 degrees C. We can vary the temperature and see the kind of effect it has. So yeah, temperature is an important parameter here, as well as density.
All right, because what I had in mind, and I'm not sure in which direction this effect would play, but I guess it would be in favor of what you show here, is that if you expect to have a magma ocean, so I guess in this case that would be for slightly higher temperature, but then the radius of the planets, which indirectly affects the depth of the magma ocean, can have an effect on the oxygen fugacity, which in turn will have an effect on the speciation of the volatiles. And namely for smaller bodies, you would expect to be more reduced, which could turn H2O, for instance, in H2, and which will, well, I mean, I guess that's kind of an intricate problem, but it would be interesting to see in which direction that could play.
Yeah, thank you. So you mean that what's controlling the change in the oxygen fugacity, the speciation of the vapor?
Yeah, so again, that's in the case of where you would have a magma ocean. The oxygen fugacity of the magma ocean might be set by the depth of this magma ocean. And then that might affect, of course, the speciation in the atmosphere.
Mm.
And well, essentially, it's been proposed that small bodies have more reducing magma oceans and more reducing atmosphere accordingly.
Right.
So
Okay.
I guess if you go from Mars towards the moon, for instance, you would turn H2O in H2.
Mm.
But yeah, I guess it requires a bit of writing down things.
Yeah, thanks. That's an interesting point.
Tom, please go ahead and ask your question.
Hi there. Yeah, on Earth, the mantle olivine often has fluid inclusions in it. I was just curious to know whether these meteorite olivine has fluid inclusions at all in them, and how that affects the volatile contribution from these things.
Yeah, okay. So there's at least like one sample we measured a melt inclusion, and that really helped us to place a lower upper bound on the amount of water that was present in that planetary body. And yeah, several meteorites have melt inclusions that, I mean, I don't, so our way of, sorry.
I was really thinking more about fluid inclusions.
Fluid,
Like
okay.
they're water rich and also often contains carbon species too.
Yeah, I'm not sure that I've seen, I have seen maybe some void spaces. Yeah, but I don't think I've seen fluid inclusions in the samples that I looked at. Yeah, certainly in the urolites as well, I don't think we saw any melt inclusions in the main group urolites. But we're always on the lookout for inclusions. And I suppose you could use Raman or something. If you were lucky enough to find a fluid inclusion, then it would be great to characterize the volatile content of those inclusions using a technique like Raman. But our samples haven't allowed us to do that because we just haven't seen them.
Okay, so maybe they're just not as common as they are in terrestrial mantle olivines or something. Yeah,
possibly. Yeah, if we're always on the lookout for little features like that, because I mean, it would make our life a lot easier if we had just a fluid phase there. If we wanted to, yeah, it would probably dominate our volatile budget.
All right, thank you.
Thanks.
Raj, please go ahead.
Hey, great talk, Megan. One quick question, I guess this is related to your final comment in the summary that you said, well, that not all CCs are water bearing. And I suppose you are making that comment based on your observation of already processed CC materials, meaning they are differentiated, silicate differentiation happened. Would you go as far as to extend that perhaps even some of the unmelted CCs were also water poor, or maybe you're not suggesting that?
Yeah, I'm not suggesting that. I don't think. I think I'm just suggesting that if you, I think there are some studies that are leaning towards using these isotopic proxies for carbonaceous chondrite versus non-carbonaceous material as a volatile signature, assuming that the volatile rich component always follows that CC isotopic signature. And so that is potentially I think we have to remember that some of the bodies in that reservoir were differentiated and were clearly dry.
Right. Yeah. Okay. Yeah. Thanks.
Megan, I had a question as well. So basically, like you talked about in your conclusion slide, that these different, or these thermally metamorphosed or these differentiated bodies, they should have lower amount of water than that is present in the Earth. So either the water should be delivered by bodies that were smaller at an early stage, so that they escape this large scale volatile loss, or the bodies have to form little, or those bodies form a little bit later, so that you don't have any 26 element and then your size independent. But we have evidence. So what were the building blocks of Earth like? So were they all? So were they differentiated? Were they undifferent? Were they small bodies? So what would you say generally about the building blocks of Earth?
So I'm not sure that my results really speak to the whole Earth, but the volatile component has to be, I think, delivered late enough that the proto-Earth is approximately Mars size, so it can retain anything that's delivered. So I think the volatiles are delivered later on, and by unmelted material, either because that material was small or because it formed late enough that it didn't melt and didn't have enough 26 aluminum in it.
Like you could even have larger bodies where the crusts of those bodies escape differentiation, and so you basically have this crustal material that is undifferentiated and is primitive, and internally you could have a largely differentiated body. So you could, maybe I think it would be possible that you can actually kind of have larger bodies as well. So you don't have to like have an undifferentiated body, you just have to have some undifferentiated material in a body to deliver it.
That's right. Yeah. And probably to escape full melting and differentiation, those bodies that we think might only be partially melted were maybe the ones that were forming a bit later.
Okay.
Yeah, but certainly I like this idea that you have this unmelted crust on top of a heated interior. Well, also things like Ceres, and we've got bodies out there that have undergone ice silicate differentiation as well, that are also obviously a viable source because they're out there.
Yeah.
Yeah.
Are there any other questions from the audience?
Well,
yeah. Okay. Yeah. Go ahead.
Yeah, I had another quick question, which is more detailed. But I was wondering, when you showed the water contents in urelite in the olivine and clinopyroxene, it seemed that clinopyroxene tend to have lower content, which seems to contradict the higher partition coefficient. So I was wondering whether you could comment on that.
Yeah, you were listening in the quiz. Okay, yeah, that's a very astute observation. And the short answer is that I think we're coming up against our detection limit. And so we do not have equilibrium partitioning between CPX and urolite and olivine in these urolites. Because if we did, then if the CPX contains 6 parts per million water, we'd expect the olivines to contain less than around 0.6 parts per million water. And that is below our detection limit. So we're not going to be able to resolve that difference. And so, yeah, this is why I'm reporting these as kind of upper bounds. I think we are, the true value of the water in the olivine could be lower, but we're not able to measure that difference.
Okay, all right. Yeah, thanks.
All right. I'd like to thank Megan again for presenting her amazing research today. Thank you everyone for joining, and I hope to see you next semester on the next series of Global Planet seminars. Thank you everyone.